Hello everyone, welcome to lecture 55 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture is on thermally tunable metamaterials. So here is the lecture outline. We will first have a brief introduction to the thermally tunable metamaterials. Then we will consider three examples. First we will consider vanadium dioxide VO2 based tunable metamaterials, where we will be considering thermally tunable infrared metamaterial using the phase transition of VO2, and then we will look into a thermally tunable broadband optical absorber. Next we will look into indium antimonide INSB based tunable metamaterials. We will see how thermally tunable terahertz filters can be obtained using INSB bars. Then in the end we will look into strontium titanate based tunable metamaterials. There we will see how tunable silicon based all dielectric metamaterials can be made with strontium titanate thin films to operate in terahertz range. So let us first consider the introduction towards thermally tunable metamaterials. So thermally tunable metamaterials basically offers active control over electromagnetic response by modulating material properties through temperature variation. That is where the name is thermally tunable metamaterials. So this kind of materials basically enable dynamic control of resonance, absorption and wave propagation. So what is the working principle? Here the dielectric response is basically tuned by temperature induced changes in either the dielectric constant or electrical conductivity or the phase state of incorporated materials. So this will basically lead to tunable resonant behavior of the metamaterials. So as you can understand, okay, here you can see a schematic of a thermally tunable metamaterial, which is basically based on a dielectric substrate, on top of which there are some gold based resonators, square resonators, and then you also have some thermally responsive materials placed in between. So these materials will have some change in their properties like dielectric constant, electrical conductivity or the phase state, that will effectively change the resonance behavior of this entire metamaterial under heat, and that is how this will give you tunable behavior or response. So what is the tuning mechanism? It can be passive heating like ambient or Joule heating. Okay. So Joule heating basically occurs when a current I flows through a conductor that has got a resistance of R, causing the material to heat up, okay, due to collisions between the charge carriers such as electrons, right. So when voltage is applied across a resistor, electrons gain kinetic energy, and as they move through the lattice of atoms in the conductor, they will basically collide and lose energy in the form of thermal vibration or heat, and that will basically increase the temperature of the material. So this is one mechanism, that is passive heating. There is another one that is called active thermal control, that can be done using either microheaters or laser pulses heating. Okay. So what is the effect of thermal tuning? It basically introduces a shift in the resonance frequency of the metamaterial. So that allows modulation of absorption, reflection and the transmission characteristics of electromagnetic waves falling on this particular metamaterial structure. Okay. So you can also switch the metamaterial between different functional states. So it can be transparent to the incident electromagnetic wave, or it can be a absorber. So you can actually switch between the two states. So what are the common thermally responsive materials which are showing promising applications in this field of tunable metamaterials? The first thing that will come to your mind is a phase change material called vanadium dioxide. So, this basically undergoes a insulated to metal transition near 68 degree temperature, okay, 68 degrees centigrade. There are other materials like semiconductors like silicon or indium antimonide, okay. So, they basically have temperature dependent carrier density, so that also affect their dielectric properties, okay, or the conductivity, right. And then you have thermally sensitive oxide like strontium titanate. So, basically they exhibit large temperature dependent dielectric permittivity, right. So, this is phase change, this has got a temperature dependent carrier density, and this has got temperature dependent dielectric permittivity. So, we will now take each of these material in one example and see how we can make thermally tunable metamaterials from this kind of materials. So, first thing you have to understand that why we are doing this. The advantages that you get from thermally tunable metamaterial is that you do not need complex circuitry like a electrically tuned system, okay. It actually allows smooth and reversible tuning. Moreover, it also is compatible to miniaturized and integrated platform. However, all is not good. There are some challenges associated to this thermal tuning procedure. The first thing is the response time is slow as compared to electrical tuning, and then as you are applying heat, so there are issues with heat management and localized control, and there could be thermal fatigue and material degradation over multiple cycles. Despite all this, they are popularly used in different applications such as reconfigurable absorbers, thermal camouflage and cloaking, infrared detectors and smart windows, switchable filters and sensors, also tunable antennas and beam steering devices. So, with that, let us first go into the first type of thermally tunable metamaterial, that is a phase change material based design. So, we will consider a vanadium dioxide based tunable metamaterial. So, here VO2 or vanadium dioxide is a metal oxide which is popularly known for its temperature sensitive phase transition properties, and the temperature you need to keep in mind is 68 degrees centigrade, that is around 341 Kelvin, right. So, what happens there? Phase transition takes place from dielectric to metal. So, vanadium dioxide changes from a dielectric state to metallic state at this temperature. So, this allows easy tuning with heat, okay. So, the tuning mechanism remains like this, that the magnetic resonance is excited through phase transition of vanadium dioxide, and this magnetic resonance in metamaterials basically occur when an external electromagnetic field interact with the magnetic resonance that is excited within the metamaterial structure. So, large tunability can be seen due to different magnetic resonance excitation conditions in the two phases of VO2. So, in the metallic phase of VO2, you can understand that the magnetic resonance is basically assisted by the plasmons, whereas in the case of dielectric phase of VO2, the magnetic resonance is basically driven by the optical phonons, okay. So, here we will see a thermally tunable infrared metamaterial that is based on this phase transition of VO2. So, this is a design of a wavelength tunable infrared metamaterial. So, the mechanism that is shown here says that an electromagnetic wave's magnetic field interacts with the magnetic element of the metamaterial that excites the resonance. So, in this particular structure you can see you have VO2, then you have a dielectric magnesium fluoride, and then again you have 1D strips of VO2 which has got a width of W and periodicity of capital lambda. So, this is the height, then you have D1 thickness and D2 thickness of the two layers. This is the direction of the incident electromagnetic field. So, the electric field is along the width of the strips and the magnetic field is along the length of the strip, okay. Now, because of this kind of magnetic coupling, that basically leads to strong absorption or emission of the wave at particular resonance frequency, right. So, we have already seen the metamaterial structure. This is nothing but a one dimensional VO2 periodic grating that is lying on a stack of magnesium fluoride and VO2 films. So, here are the parameters that are considered in this particular example. Lambda, capital lambda, the periodicity is considered to be 1.5 micron, the strip width W is 1.25 micron. The thickness of the VO2 grating, that is H equals 0.5 micron, thickness of this magnesium fluoride film is 0.3 micron and the VO2 film is 1 micron. Okay. And this structure, okay, because it is based on VO2, so the temperature of the structure that can be modulated to thermally control the VO2 phase transition, which basically occurs at 68 degree centigrade, right. Now, if you look into the material properties of VO2, for temperature above 68 degree centigrade, it is basically in metallic phase. So, VO2 behaves like an isotropic metal. Okay. So, you can describe its electrical permittivity using the popular Drude model. So, you can write epsilon m as a function of omega will be epsilon infinity minus omega p square divided by omega square plus I gamma omega, right. So, omega is basically the angular frequency, epsilon infinity is the high frequency constant, omega p is the plasma frequency and gamma is the collision frequency, right. Now, the dielectric phase will basically occur for temperature below 68 degree centigrade. There VO2 basically becomes a uniaxially anisotropic dielectric. So, its behavior is described based on the orientation of its crystal structure, because it is a uniaxial material. So, for a 200 kind of oriented crystal with its optical axis normal to the surface, it basically shows two responses. Ordinary response epsilon O will occur when the electric field is basically perpendicular to the optic axis, and extraordinary response that is epsilon E will occur when the electric field is parallel to the optical axis. So, both of these components can be described by a classical oscillator model. So, you can use this particular model. Okay. So, epsilon omega equals epsilon infinity plus summation over j equals 1 to n. So, these are the number of oscillators that you are adding. Okay. S j omega j square divided by omega j square minus I gamma j omega minus omega square. So, omega j is nothing but the phonon vibration frequency, gamma j is the scattering rate, S j represents the collision frequency or the strength, collision strength, not frequency, and j is basically the phonon mode index. Okay. So, for the metallic phase, that is given by the Drude permittivity, there we have considered epsilon that is given in that equation 1, right, previously we have seen. So, there the infinity or the high frequency permittivity epsilon infinity is given as 9, omega p is considered 8000 centimeter inverse and gamma is basically 10,000 centimeter inverse. Now, with this kind of data, you can put the values of this permittivity. We are basically plotting the real part of the permittivity as a function of lambda here. So, the blue curve shows the dielectric VO2's ordinary permittivity, and this red dotted curve basically shows the extraordinary permittivity, and this is how the metallic VO2 permittivity looks like over this particular range. So, what you see here is that for the metallic phase you basically have a negative real permittivity enabling plasmonic resonances, which is similar to noble metal, and for the dielectric phase multiple phonon modes can be seen in both ordinary and extraordinary components. Okay. Here also you can get some negative permittivity that you can see in both ordinary as well as in extraordinary refractive index, so or permittivity. So, epsilon O between 12.4 and 16.7 micron you have negative values. For epsilon E you have negative values between 17.5 and 18.8 micron, right. So, here we see the thermal tunability details. So, when VO2 acts as a metal, that is the temperature is above 68 degrees, okay, you can see that there is a broad, so metallic phase is this one, dotted one, as you can see. You see a broad absorption peak is appearing at 10.9 micron, okay, and for VO2 working as a dielectric, that is for temperature below 68 degrees centigrade, this absorption peak is basically shifting to 15.1 micrometer. So, you can see there is a wide tunability, and if you find out the percentage tunability, that is the lambda dielectric minus lambda metal over lambda metal into 100%, that comes out to be 38.5%, and that is a very large tunability of the resonance wavelength, okay. So, this basically implies that the resonance wavelength can shift by up to 38.5% when the VO2 switches from metallic to dielectric phase. So, such a large shift is basically significant for thermally tunable metamaterials, as this is basically enabling wide range wavelength reconfigurability. So, now let us look into another design which is again based on VO2, okay, but this time we are making a thermally tunable broadband optical absorber. So, this design basically uses patterned plasmonic metasurface with thermochromic VO2 spacers, as you can see here, okay. So, the structure is basically, so I am just, this is the schematic of the structure. A shows the insulating phase and this is the metallic phase of the structure. So, these are the temperature for 25 degree, this is for 80 degree, the structure remains same. It is basically a chromium, then you have VO2 in insulator phase here, and then again you have chromium, okay. This is the stack, and then you have different width of this subcells which are repeated. The surrounding medium is air, okay. The same thing is here, just that because the temperature raised up, so VO2 is right now in metallic phase, okay. So, the values of the geometric parameters are given here. The period is around 1900 nanometer. There are different widths of the subcells W1, W2, W3, W4, and similarly here their gaps are also mentioned, G1, G2, G3, okay, and the thicknesses of the different layers are given, okay. So, what is the tuning mechanism in this case? The absorber's properties are basically dynamically tuned using the insulating metallic phase transition of VO2, which is essentially triggered by temperature change, right. So, let us analyze this, what is happening. If you consider room temperature, that is 25 degrees centigrade, VO2 is in the dielectric phase, right. So, the absorber basically here functions like a metal dielectric, metal kind of a structure, right. So, you can see the blue curve, that is for 25 degrees centigrade. So, you can see that you are getting a very high or broadband, very high ultra broadband absorption. So, you can see the bandwidth, if you consider absorption greater than 0.9, you are getting the bandwidth more than like 3000 nanometer, that is starting from 1620 7 to 4696, and the average absorption in this range is around, it's more than 93.5%, and the peak one is around 97.6%, right. So, you get almost near perfect absorption in this range 3173 to 3404 nanometer, okay, and you have got the peak around here. Now, what happens when you increase the temperature at 80 degrees centigrade? If you again measure the same thing, you will see that now it has converted into metallic phase. So, now the structure has become essentially all metal kind of metamaterial. So, what happens? The absorption peak becomes very narrow, okay, it is only 1443 to 2066. So, the bandwidth above 0.9 absorption is only 623 nanometer. So the average absorption basically increases here, but the bandwidth has dramatically reduced. The peak absorption is also recorded to be 99.4%, that is at 1706 nanometer. So what we see here is that these are the two cases, and here also you can find out for different temperature. These values are plotted to just to show you how the transition has happened from 25 degree to 80 degree. Okay, so this graph basically shows you how the transition takes place, right. So this basically allows you to achieve a simultaneous and active tuning of both absorption bandwidth and the peak resonant wavelength in the near to mid infrared region. Okay. So that is having a lot of application. So that is why this kind of metamaterials are very useful. Next we look into the other type of metamaterial, that is indium antimonide based tunable metamaterials. So why we study these metamaterials? Because if you look into the traditional terahertz devices, there are limitations in the form of metallic sub-wavelength hole arrays. Okay. So there the metallic sub-wavelength hole arrays basically offer peak transmissions and low losses in terahertz range, but intrinsically they are passive, means their intrinsic nature cannot be changed by electrical, optical or thermal methods, meaning that the terahertz transmission cannot be actively controlled. On the other hand, if you consider semiconductors like gallium arsenide and indium antimonide, okay, they can have carrier concentration changed by external stimuli, just like using electrical, optical or thermal excitation that can modulate the intensity of the transmission peaks. Unfortunately, these also suffer some sort of drawbacks. So one could be that you have low peak transmission, because semiconductors have inherent material losses in the terahertz regime that leads to transmission of less than 30%, and there is no frequency tuning. So the peak transmission location cannot be tuned, only its intensity can be modulated. So what you require, you basically can see that there is a requirement of active tunability in both frequency and intensity, right. So that is where the solution comes to make hybrid metamaterials. That is where you incorporate semiconductors into metallic structures that basically enables broadband filtering and also ensures large blue shift of the resonance frequency by introducing temperature control. So let us see how it is done. So since semiconductors have temperature dependent permittivity, so they are basically more flexible than metal. So here you can see the design of a B shaped, okay, this is a B shaped, you can see like this, it is a B shaped metallic hole array. So this is the unit cell design and this is the overall device structure, okay, which has got thermally tunable indium antimonide. Okay. So you can see that the filter's metallic hole array is basically made of copper, and there are some thermally tuning medium placed in between, which is basically the indium antimonide. Now why did we choose indium antimonide? It is because of its electromagnetic properties are highly sensitive to the temperature changes. So how it changed? So if you consider temperature between 160 Kelvin and 350 Kelvin, the complex values relative permittivity of the indium antimonide is given by the simple Drude model. So you can consider this model, which is epsilon m omega equal to epsilon infinity minus omega p square by omega square plus I gamma omega. We have seen this couple of times. So here what is important is that the key parameter for tuning is this plasma frequency, because the plasma frequency is directly related to the intrinsic carrier density of indium antimonide by this formula, because omega p is related to n by square root of n e square by epsilon naught m conjugate, okay, or m star. So, unlike copper, the plasma frequency of indium antimonide increases exponentially with temperature. This is because N in case of indium antimonide is basically temperature dependent, right. So, you can actually express the dependency. So, N is basically carrier density. So, it is expressed in per meter cube. Okay. So, it basically obeys this formula that N equals 5.76 into 10 to the power 20 T to the power 1.5, and then you have exponential minus 0.26 divided by 2 kBT. Kb is the Boltzmann constant and T is the temperature in Kelvin. So, you can see that there is a temperature dependence, and the damping constant gamma is given as E divided by m star mu. Mu is basically the electron mobility, which is also temperature dependent. So, for large temperature changes, you will see that gamma also changes, and that also influences the absorption properties of the indium antimonide. Okay. So, if you carefully look into the structure, you can see that there is a sub wavelength B shaped metallic hole, okay, that is placed hole array filter, okay, and that is embedded in an thermally tunable indium antimonide bar. So, you can consider L to be 120 micron, D is basically this one, the width or thickness, that is 20 micron, small l is this length, okay, that is 68 micron, H is 88 micron, and small d, okay, is 10 micron. Okay, and then you will see that the periodicity is 120 micron in a square lattice. This is the unit cell that is repeated to make the device. So, what is happening here? So, because of this embedded thermally tunable indium antimonide semiconductor bar, okay, so in this particular device you also can get temperature control, okay, via this indium antimonide, because it changes the electrical property of the structure. So, the resonance frequency of this filter can be actively tuned by controlling the temperature of the indium antimonide. So, if you consider a p polarized terahertz wave, which is normally incident on the structure, so you can see from the FDTD simulation that with different temperature, the black is 350 K and this side it is 160 K, and this is the transmission graph. So, you can see from 350 to 160 K you can tune the transmission, okay, heavily between say 2 point or around 2 terahertz to somewhere 0.7 terahertz, right. So, you can also see the values that at a low temperature 160 Kelvin, indium antimonide basically acts as a dielectric, where you have low carrier density of 0.94 into 10 to the power 20 per meter cube, and you are getting a transmission peak of 91% at 0.74 terahertz. Whereas, when you go to moderate temperature like 390 Kelvin, which is basically this one, the dotted one. So, there it starts showing a metallic property, and you can see the carrier concentration is much higher, 1.57 into 10 to the power 22 per meter cube, and there the transmission peak is around 84.5% at 1.71 terahertz. So, there is a huge blue shift. And if you go to further high temperature like 350 Kelvin, the carrier concentration further increases 5.76 into 10 to the power 22 per meter cube, and you have got a transmission peak of 89.1% at 2 terahertz, right. So, overall performance, you can see that you can tune from 0.74 to 2 terahertz, okay, that is like 173% broadband blue shift, and the transmission drop is only around 3% at the original resonance frequency, that is at 0.74 terahertz. Now, let us briefly look into the last material for today's. So, that is strontium titanate based tunable metamaterial. So, here we consider a tunable silicon based all dielectric metamaterials or SAM, okay, with strontium titanate thin film in the terahertz range. So, what are the advantages of the silicon based all dielectric metamaterial? They are basically low loss and they have simple structure. However, they have some limitations in the form of narrow bandwidth and low tunability that basically restricts their practical application. So, the solution is that you can make a tunable SAM in terahertz range, and this can be achieved by covering a SAM. So, this is basically a silicon based all dielectric metamaterial, and here you can see that you are basically covering that with STO, okay, as an active layer, and that is giving you that tunable metamaterial. So, the tuning mechanism here is that the terahertz response of this kind of all dielectric metamaterials, silicon all dielectric metamaterials, can be thermally tuned, and it is possible because STO is a material that has got a temperature dependent permittivity. That means the electrical properties basically change with temperature. Okay. So, what you have done, here you can closely see that the structure is basically having a silicon 1D grating that is designed for the terahertz range. Okay, these are nothing but a periodic array of silicon rods. Okay, and this is the unit cell design. So, the magnetic field of the incident terahertz is basically considered along the length of the rods, and this is the cross section that shows you the periodicity is considered to be 200 micron, and the size of the rod is 100 by 100 micron. And the resonance behavior shows that this high refractive index and low loss of silicon can allow it can induce magnetic resonance in the structure, and because you have STO, which has got a frequency dependent complex relative permittivity that can be expressed like this: epsilon omega equals epsilon infinity plus f divided by omega naught square minus omega square minus I comma omega, where epsilon infinity is basically the high frequency bulk permittivity, here considered as 9.6. F is the oscillator strength and omega is the angular frequency. Okay. Here omega naught and gamma are basically the soft mode frequency and the damping factor that is expressed in terms of temperature. So, you can see that these two are basically temperature dependent parameter, and that is why STO has a temperature dependent complex relative permittivity. Okay. And because of this, it is providing that tunability in the silicon all dielectric metamaterial structure. So, once you analyze this grating structure by calculating or simulating the transmission curve, so here you can see without STO the black curve shows the transmission. You basically have two resonance dips. The first one is around 0.68 terahertz, that is from the linear enhanced magnetic field induced inside the rod, that is basically the first magnetic resonance mode, and the second one is around 0.903 terahertz. This is the coming from the two opposite linear magnetic fields inside rod. So, that is basically giving the second magnetic resonance mode. Now, when you apply the STO films, that is basically you are putting a 500 nanometer thick layer of STO on the surface of the silicon grating. There, when you change the temperature, you will see that there you are basically able to move these dips to lower frequencies. So, you can actually calculate the change in the relative permittivity of the STO with temperature using the equations that you have seen earlier. So, here you can see that both the resonant dips are basically getting a redshift, that means they are shifting to lower frequencies, and that is mainly because of the increased thickness of the STO layer. And you can also do it for when you change the temperature for the same thickness, you are again able to see that similar kind of shift. So, that means you can get dynamic control of the resonance frequency using temperature as a tool. So, this is how we can make thermally tunable metamaterials. So, with that we conclude this lecture. If you got any query, you can always drop an email to this email address mentioning the course number and the lecture name on the subject line. Thank you.